And the test that I chose is a chapter 6 test from 2023. When you guys were in grade 8, from 23, that's when you were in grade 8. Okay. Here are some of my files, just to show you. With M11 file number 2. So let's see if I can find the 2023 chapter 6 test. Here's chapter 6 test. 2023, just to get an idea. Now, the intent is, so you're not going to try to write this down. Just getting a buffet of the types of questions I can ask. All atoms, remember, chapter 6 is periodic tables, periodic trends, chemical bonding, Lewis structures, shaping behavior molecules, right? All atoms with 7 valence electrons. What atoms have 7 valence electrons? What family? Halogen, right? H, A, L, N, G, N. 7 valence electrons. You need to be able to remember that, right? All halogens, that's what that question is saying. They don't conduct electricity well. Metals do, but they don't, and they're not solids. They never form cations because they never give electrons away. And they're not all gases at room temperature and react only with difficulty. That's the noble gases. That would be metals. It's B. They're the most reactive elements in the table, and all diatomic free elements. F2, Cl2, Br2. Yeah. Now, if you don't connect that to halogens, too bad. Most transition metal atoms have 2 electrons in their outermost s something. Remember, we always start filling the outer s and then go back to the T, so that's it. They don't have filled valence shells, so they're noble gases. They're not the most reactive elements in there. There is the alkali metals. And they never form anything. Ever. Metals never form anything. An element with an electron configuration of that. Well, that's obviously an alkali metal. Which alkali metal? 10N1 is 11, sodium. So that first part is just saying sodium would most likely react to form an ionic compound. Pick a halogen. Anything that's S2P5 is a halogen. S2P6 is a noble gas. Anything S1, that's another alkali metal. And S2, that's helium. That never reacts with anything. So pick a halogen. Alkali metals and halogens always form ion. Moving down a chemical family, the ionization energy tends to go down. But atoms get bigger. That's one of the trends. We go down as atoms get bigger, ionization energy decreases because the outer electron cloud is held less and less tightly. That trend is due to all of the following except. Well, as we go down a family, there's effective shielding. You see the number of clouds between the outer electrons and the nucleus. Atoms are getting bigger. Electron-electron repulsion is increasing. Because remember, that's a component of shielding. Ineffective shielding is true. Oh, that's left to right. That's why atoms get small. Moving right across the chemical period, ion and energy tends to go up. Why? Because atoms get small. That trend is due to all of the following except. Well, left to right, nuclear charge goes up. Yeah, that's the fire getting brighter and brighter. Okay. Increasing atomic size. Size goes down left to right. Ineffective shielding. Yeah, left to right, there is ineffective. So that applies. Increasing nuclear attraction for valence electrons. That's why they get small. So that's removed. They don't get bigger, they get small. What about 8? This is taken right out of a set of review questions. Try 8 and 9. Let's say you saw that on the final exam. You don't have to write it down, just guess an answer. What happens when I take electrons away? The things get, what I have left, get bigger or smaller? Remember the two things that dictate atomic size? Attractive force is the electron field for the nucleus. Repulsive force is the electron field for each other. If I take an electron away, what's left is feeling more of attraction. So less electrons, so there's less repulsion. That's going to make it smaller. So it can't be A or C because it's always small. If it's smaller, it must mean the nuclear attraction has gone up and the electron-electron repulsion has gone down. Exact opposite is true for an atom. Every time I add an electron, because someone's showing up last minute, he only got one pizza. You got to divide it into smaller pieces. The more electrons I add, the less attraction each electron field produces. The more electrons that are there, the more repulsion. That was taken right out of the review question. An anion is always larger than its neutral atom due to reduced nuclear attraction and increased electron-electron repulsion. And if you think about it, that has to make sense. The more electrons I put there, the more repulsion. The more electrons are there, the less repulsion. Three consecutive elements in a table in order of increasing atomic number have these first ionization. The trend in ionization. Three numbers. Pretty big, bigger. Right, where does that happen? Where do you see that trend in ionization energy? Going to a maximum energy. Where's that happen? Left to right, what happens to ionization energy? It goes up, right? To a maximum of what? What's the highest ionization energy that appears? Noble gases. What's next? Alpha 11. So it can't be this one because neon has a higher ionization energy. Can't be this one because after neon, the ionization energy would go way down. It's going up with the second element. It should be C. Fluorine's high, neon's higher. But then after that period, you start the next. So it always increases to a maximum of the noble gases and then dies when we get to the alpha elements. Notice you don't have to memorize anything. You just have to say, okay, what's the trend here? Remember, that was section 6.2. Which of the following compounds has the greatest ionic character? Greatest delta En. Biggest atom, smallest atom. A. Lowermost left, uppermost right. In a chemical bond, the greater the delta En between the bonding atoms, the more polar the bond. Yeah. All backwards. Not the less ion the bond, the more ion. Not the more equal the electron sharing, the less equal the electron sharing. Not the more covalent, the less covalent. So it's A. Substances composed of polar molecules tend to exhibit, well, if they're polar, they want to stick together. And if they want to stick together, we would accept the boiling points to be higher than expected. This and this and this don't answer the question. Less attraction than usual? No, more attraction because they're polar. Weaker intermolecular forces? No, stronger. Lower bond energies, that's got nothing to do with it. Bonds are inside, not between them. Assuming identical peripheral atoms in polar bonds. Which of the following molecule types will not have a molecular diagram? So we started the classroom. So if you've got a lone pair or pairs in the central atom, and let's say all the X's are the same, which AXMEN notation that has lone pairs is symmetrical? That's T-shaped. That's not. That's square pyramidal. That's not. That's water. That's Bishop. That's square planar. AX42. Again, taken right off one of the tracking points. Is there a memory component there? Okay, there is. There always is some studies. CH4 molecule is non-polar. There's only one nitrogen gas. It's not of this form. The bonds are polar, 225, 241, and obviously by fourth birth of that, it can't be a triangle. All of the individual bond atoms cancel. Okay, so AX4, all the X's at sigma. Intermolecular forces do not include covalent bonds. Those are those are inside. Which of the following attractive forces is the strongest? A lot of students, by the time they finish reading that, they go on, they pick hydrogen bonds. The answer is D. Covalent bonds are stronger than any intermolecular force. Hydrogen bonds are stronger than other intermolecular. But no hydrogen bond is as strong as a chemical bond. So covalent bonds are much stronger than these. When nonpolar molecules attract each other, intermolecular attractive forces result from London dispersion forces. And those are always there. In which of the following is the carbon-carbon bond distance the greatest? Well, remember, double bonds are shorter than single, triple bonds are shorter than double. So the shortest would be this one, but the greatest would be this one. Obviously, the more electrons we pack between nuclei, the shorter the bond because of more attractive forces. Electron pair repulsion interactions listed from weakest to strongest. And the bond pairs take up the least room, lone pairs take up the most room. So lone pair has to be the greatest. That's the only thing you look at. This is the right answer. Bond pair is less intense than lone pair, which are less intense than lone pair. 21 should ring a bell. Experimental evidence for bonding in the carbonate ion shows 3 identical carbon-oxygen bonds, which are intermediate in strength, length, and reactivity between single and double bonds. This results from a phenomenon called resonance. Delocalized electrons. Which of the following molecules has exactly 2 lone pairs of electrons on the underlying atom? It's like H2O. S is an oxygen group, so H2S, 1 and 2. So there's no lone pairs, that is 1, that is 3. All Q of the form AX4E. Assume which of the following. That'll be square pyramidal. No, sorry. That'll be C sub. And you have to draw it. And that's a memory. Which of the following would not demonstrate hydrogen bond? Hydrogen has to be in a polar molecule and connected to nitrogen, oxygen, or fluorine. Not chlorine. Notice that chlorine has the same electroactivity with nitrogen. It's just too big. Okay. So that's the multiple choice. Here's the this is taken from section 6. We would expect sulfur's first ionization energy to be greater than that of phosphorus because it's small. However, sulfur's first ionization energy is actually less. Explain why this is true using equals of dyes and each. You need phosphorus in colloidal dyes. You get to the 3p, you're going to do this. No paired electrons can be separate. when you get to sulfur, you have that. That extra electron repulsion is why the ionization is a little less. Same is true for nitrogen to oxygen, right out of the picture. Okay. Here's the table I've been referring to. Ask yourself how much of this you could do today. First column, here's the formula. Give it an AXMEN label. Geometry, name and diagram. Type of intermolecular force. Would you guys draw that little paper? I'm not gonna take time for units, but if you did it, this. Sulfur's already expanded on potential. Okay. It only needs 2 more electrons, but it's got 4 extra. So it's already expanded off that. That's it from atom. Draw the structure. Well, that's seesaw. Remember, in 5-coordinate systems, 1 is 5. An equatorial, we got axial. You never put the lone pairs axial. Let's put E here. Playing the board. Let's put one of the X's coming out of the board. That. And by drawing the central atom open like that, you can kind of show that thing in front. And then the other one, and again, that's seesaw. And look at the molecule, it's not polar. So the bond dipoles don't cancel, which means it would be dipole-dipole. Notice I've said intermolecular force acting. Is there more than one intermolecular force acting? What's always there? It's the London dispersion. So no matter what the shape of the molecule, London dispersion is there. So this would be dipole-dipole and London. Okay. And I sometimes say just London forces, but I'm going to just give it one name, dispersion. Just London forces. London dispersion is the correct name. And IF5, again, same thing. I can't give you 7 or 8 of these, but I could give you a couple. And that's 2 sections in one lecture. Dot structure, shape, behavior. Okay. Number 3. Carbonate ion can be represented by 3 resonance structures. Draw them, including the electrons involved in the resonance. So each of the diagrams drawn correctly would be 1 each, and then the electrons involved in the resonance, you get an extra one. This is taken right out of the book. Each of the following molecules have 4 pairs of electrons associated with the central atom, which is in bold 3. Explain it in the differences in the following coordinates. Well, AX4 is only going to identify no lone pairs of the central atom. No interactions with one pair bond. Nitrogen AX3E, smaller. Oxygen AX2B2 even smaller. And then I've asked you to use diagrams down here, basically saying, well, lone pair more intense, Bond pair, more intensive bond pair. The diagrams should tell you that. And I put this as a bonus. I won't worry about it for now. I might show you next class. But this is not